Okay, so then let us look at some examples. Okay. So, this question says find the Z transform of f of z given by z square minus 6z plus 8. Okay. So, to find the Z transform, again we see that the denominator could be factored as two linear factors. So, let me factor out. So, f of z will be z divided by z minus 2 times z minus 4. I see that this factor is also, I can now break it down using the method of partial fractions, that this rational function is also the following. So, I am just using the result directly. Students can see that these two partial fractions indeed when added up in this way will give me this function to which I began with, So, now all I have to do is to find the inverse transform of these two following rational functions. Okay, so, then to find the inverse transform, let me call it as f of n, which is the inverse transform of capital F. This is nothing but half of the Z transform. So, I can take this factor out because Z transform is even the inverse transform is a linear operator. So, this becomes inverse transform of Z by Z minus 4 minus the inverse transform of Z by Z minus 2. Okay. So, all I have to do is to find the inverse transform of these two functions, which can be found right away. So, now if students recall that the Z transform of Z divided by the inverse transform of Z divided by Z minus A will be A to the power n. So, what I am trying to recall is the following result. So, recall that the Z transform of A to the power n is Z by Z minus A. Okay. So, that is the result that I am going to use to see that my f of n, that is the inverse Z transform of the following quantity 1 by 2 Z transform of Z by Z minus 4 minus the inverse transform of Z by Z minus 2. Okay. I see that this is also equal to half. I am going to use the result above. I get that this is half times 4 to the power n minus 2 to the power n. Okay. So, that is what the inverse transform is for the function. Now, let me show you another example on how to use the method of convolution, how to use the method of convolution to find the inverse transform. So, the convolution method. Okay. So, the problem says find, again I am going to go back to my previous example. So, find the inverse transform of the following function z square by z minus a times z minus b. Okay. So, find the convolution of, find the inverse transform of this following function. Notice that I can write my quantity inside this whole rational function as follows. So, my question that is asked is the following. This is also equal to the z inverse transform of z by z minus a times the z by z minus b. So, I have just rewritten it as a product of two factors. Now, notice that this is also the z transform, let me call this as the z transform of a to the power n, and this quantity is the z transform of b to the power n, and I am trying to find the inverse transform of the product of two z transforms. So, the result will be nothing but the convolution of the following products. so the convolution of the following two functions. So, m from 0 to n, f of a, well, f is my a to the power n. So, a to the power n minus m, b to the power m, and this summation. So, that will be my inverse transform. Result is found right away from convolution. Now, I can process this a little bit more to see that this is also equal to a to the power n summation m from 0 to n times b by a to the power m. Okay. So, then if I were to take this summation, this notice that this is a finite sum, I can sum it up. This is a finite geometric sum. So, this finite geometric sum is a to the power m, a to the power n, 1 minus b by a to the power n plus 1 divided by 1 minus b by a. And then when I slightly simplify this entire expression, I get my answer. So, this is also equal to a to the power n plus 1 divided by a minus b times 1 minus b by a to the power n plus 1. Okay. So, that is my, so we see that, well, this particular problem could also be solved using method of partial fractions, but I saw that in particular using convolution the answer was quite easy to find. Okay. So, the choice depends on the student which method to use. The idea is to simplify your example as much as possible. Okay. So, then let me show you another example. So, the second example tells me, well, the fifth example tells me that find the inverse transform of, well, the inverse Z transform of the following function. The function is given by 3 z square minus z divided by that factor z minus 1 times z minus 2 square. Okay. Now, we can see that this is not a very trivial product of two functions. We cannot use the method of convolution right away, because we can see that this is not the well known or a trivial product of any two functions. So, I am going to use my method of partial fractions. So, I am going to break this expression into some simple partial fractions. So, let me write down the result. Students can verify that this f of z is also equal to the following partial fractions. So, I get the following terms on the right hand side. So, 2 times z by z minus 1 minus 2 times z by z minus 2 plus 5 by 2 times z divided by z minus 2 square. Okay. So, the idea is we can break it down into 3 partial fractions, one in which the denominator is this linear factor, the second in which the denominator has another linear factor, and the third in which the denominator has this quadratic factor. So, that is the standard way of dividing in partial fractions. Okay. So, then if I were to take the inverse, of this function given by f of n, so this is also z inverse of this function. I see that this is also equal to, well, let's evaluate the inverse transform using my result that I recalled in my previous slide. I see that the first inverse transform of the first term will be 2 times 1 to the power n. So, here my a is 1 minus 2 times 2 to the power n. So, that is my second term, and then plus 5 by 2 times this following quantity is the inverse is the, so this is the Z transform of, well, let me just say that this is the inverse transform of the Z transform of n times 2 to the power n. So, this result has already been shown that this quantity 2 z by z minus a square is the Z transform of n times a to the power n. So, we did it in one of our previous examples. Okay, so, then I get the let me just simplify this expression, I get the following. So, this is 2 minus 2 to the power n plus 1 plus 5 by 2 then times n to the power n, n times 2 to the power n, and let me just simplify this further. I can cancel a 2 out and put a change the factor here. Okay, so at this point my example is complete. So, what I have is the following result. I have that this is also 2 times 1 minus 2 to the power n plus 5 n times 2 to the power n minus 1. So, that is my answer to the problem raised. So, we see that depending on the problem, it is up to the students to use whichever method is found to be convenient. So, we saw that in this example convolution was not very convenient because we cannot break it down into simpler products of two rational functions. So, it turns out that partial fraction was the way to go in this example. So, then let me look at another example. So, I am going to now I have specifically mentioned to use convolution method in this example. So, use convolution theorem to show the following. I need to show that the inverse transform of z times z plus 1 divided by z minus 1 cube is n square. So, I need to show using the method of convolution. Okay. So, then which means I need to break this quantity inside into the product of two simpler quantities for which I can find the inverse transform. Okay. So, let us look at that step. So, what I am saying is the inverse transform of this quantity z times z plus 1 divided by z minus 1 cube. This can also be written as the inverse transform of the following two products z by z minus 1 square. So, I know I can find the inverse transform of this factor times z plus 1 divided by z minus 1. Okay. So, notice that if I choose my f of z, so choose my f of z to be this factor z by z minus 1 square and my other function g of z to be the other factor z plus 1 by z minus 1. I can see that the inverse transform of this factor is the inverse transform of capital F of z is f of n, let me call this f of n, this is n. So, I am right away using my result. So, this is n times 1 to the power n or this is n. Okay. Now, to find the inverse transform of this particular function, notice that this function is also z by z minus 1 plus 1 by z minus 1. So, I have broken down the numerator to write this rational function into the sum of two partial fractions. Now, notice that if I were to use my series method, so if I were to use series method described earlier, and all I need to do is expand each of these fractions appropriately in an infinite sum and find the coefficient of z to the power negative n. So, when I do that I see, so let me just divide this part of the paper so that students are not confused. So, here my function g of n, which will be the inverse transform of g of z, will be the inverse transform of these two factors, these two rational functions. I see that these are, all I have to do using series method is to find the coefficient of z to the power negative n, and those are respectively the Heaviside function h of n. So, the Heaviside function for the first one is h of n, the second one is h of n minus 1. So, students are requested to see that once we expand these two products in the series, all they have to do is to find the coefficient of z to the power negative n. We see that those coefficients will turn out to be 1 only when the argument of this Heaviside function is satisfied. Okay, so hence the result. So then which means that the Z transform of the quantity z times z plus 1, the quantity with which we began with, will be equal to the Z transform of f of z times g of z, right. So, this will be nothing but the convolution of f of n minus m times g of m. So, let me say m from 0 to n. So, I see that the first this finite sum is going to give me the following summation. So, let me just say that, let me just reverse my notation here. So, this is also equal to m from 0 to n f of m times g of n minus m. So, I have reversed my notation, and what I see is, after plugging in f and g, I see that this is also equal to the sum m from 0 to infinity. Now, f of m. So, what is f of m is given by n. So, this will become m, f of m is m, and then g of n minus m is h of. So, instead of the factor, the argument n, I plug in n minus m in this expression. So, I get Heaviside function of n minus m time plus Heaviside function of n minus m minus 1. Okay, so, now the sum, well, the sum is a finite sum, not sum from 0 to infinity. So, the sum is a finite sum, and the sum is taken from 0 to n. Now, we are summing over m. So, let me just break it down into two summations. The summation, the first one is m times h of n minus m plus the summation of m times h of n minus m minus 1. Okay. So, I see that, let me call this as S1 and this second sum as S2. So, let us see what is S1. So, S1 is the following sum, m from 0 to n, m times h of n minus m. So, the Heaviside function is 1 only when, so this is going to be 1 only when m is less than or equal to n. So, my summation changes as follows. So, this is sum m from 0 to n of m, okay, and I get that this summation, this finite sum is n into n plus 1 by 2. Okay. So, then S2, similarly my S2 will be summation m from 0 to n, m times this time Heaviside function of n minus m minus 1. So, this is going to be, this Heaviside function is going to be 1 if m is less than or equal to n minus 1, right. So, which means my new sum will be sum from m equal to 0 to n minus 1 of m, because at m equal to n the Heaviside function is 0. So, when I take this sum, I get the following, this is also equal to n minus 1 times n. So, just replace n here by n minus 1 to get back the summation of S2, the sum S2. So, my answer is the sum of S1 and S2, and that is going to be 1 by 2 times n plus 1 coming from the first factor and n minus 1 coming from the second factor. I can do some simplification to see that this is n times 2 times n, and after taking all the cancellations, I get my answer to be n square. So, I see that the inverse transform of this following factor z times z plus 1 divided by z minus 1 cube is this expression n square. Okay. So, then another fact that I want to highlight is the fact that the Z transform is not unique. Z transform depends upon the radius of convergence in which the series is summed. So, in my next example I am going to show you this fact. So, consider this example. So, I am given the following Z transforms and they are identical. So, let me call this f of z to be z by z minus 1, but I define my domain of convergence as mod z greater than 1, and then I define my second function again to be z by z minus 1, but this time I define my domain of convergence z is less than 1. Okay. So, then if I were to evaluate the Z transform inverse, if I were to evaluate the inverse of f, again students are requested to use the series method to see that all I have to do is to find the coefficient of z to the power negative n. In this, well, appropriately expand the series in such a way that z is greater than 1. Okay. So, when I expand the series, I see that my inverse is, let us say this is f of n, and it will be a Heaviside function, but the Heaviside function will be only 1 when n is greater than 0, okay, and this is going to be otherwise. Okay. So, otherwise implies n less than 0. Okay. Now, if I were to evaluate the Z transform of this quantity, right. So, the inverse transform of g, now g is the same function, notice that. However, the domain of convergence is different. So, which means that if I were to evaluate, if I were to find the series of g in this domain of convergence, I get a new function and g is given to be again a Heaviside function, but this time this is for different values of n. So, again this is left, this is going to be left as an exercise. So, I see that this is for n less than equal to 0 and this is going to be n for greater than 0. Okay. So, again this is going to be left as an exercise for the students to check. Okay. So, all they have to do is to expand these two rational functions using the series method. So, expand the infinite series, see what happens to the coefficient of z to the power negative n under this domain of convergence in both the cases. So, these are the results that we are going to get. So, which means the moral of my discussion is that the Z transform, the inverse transforms are or is not unique. So, the moral of this result is that my inverse transform is unique dependent on the domain of convergence. Okay. So, if I define if my domain of convergence is identical, then my Z transform will be the same, otherwise we may get different answers. Okay. Okay. So, moving on, let me just give now applications of Z transform. So, I am going to highlight some applications of Z transform. So, as we know that Z transforms are discrete sums. So, a natural choice of an application for Z transform is in finite differences, right, or we will see that finite difference equations is going to use heavily the setup of Z transform. So, let us now look at one example. So, I am given a first order differential, a difference equation, a first order difference equation. I see that this is, we need to solve the following initial value problem. The initial value problem is f of n plus 1 minus f of n, this is also equal to 1, and I am given that the initial condition is f of 0 is 0. Okay. So, I need to find f of n from this difference equation. So, let me call this as 1. Okay. So, if I apply Z transform to 1, I see that Now I am going to apply Z transform to the first function. I use my Z transform that I derived for the translation of the function. So let me just call that recalling the Z transform of f of n plus 1. Okay, so I have used the translation of the Z transform of the function at n plus 1. I see that when I apply Z transform, I get the result as follows. This is z times f of z minus f of 0, okay, minus the Z transform of f of n, which is also capital F of z, and that is also equal to the Z transform of 1, and that will be the expression z by z minus 1. I know that the inverse transform of the right hand side is 1. Okay. So then I have to find, let me just simplify this expression. So let me call this as 2. So simplify 2 to get to the following result. So I have z times f of, well, I need to find capital F of z, the Z transform of the solution. So let me just collect all the coefficient of f z. So f z times z minus 1, this is also equal to, well, f of 0 is 0 given our initial condition. So I get that f of z times z minus 1 is z by z minus 1, the right hand side. So I see that f of z, the Z transform is z by z minus 1 square. Now notice that this is the Z transform of a well known expression. So namely that I now take inverse Z transform, let me call this as 3, inverse Z transform in 3, I get back my answer. My original function f of n is the inverse transform of this expression z by z minus 1 square, and that will be n times 1 to the power n, or this is nothing but n. So I see that the solution to this difference equation is f of n is n, and indeed we can see that when I plug f of n is n and f of n plus 1 is n plus 1, well, the difference will be 1, and of course f of 0 is 0. So it indeed satisfies my differential equation, and hence the answer. Okay. So let us move ahead. A little bit more complicated example. The second problem says, again I have a first order difference equation. The equation says that I have to solve the following expression, f of n plus 1 plus 2 times f of n, this is equal to n, and I am given that f of 0 is 1. Now let us apply the Z transform. Let us say that this is my 1, apply Z transform. Let us see what happens. I apply the Z transform in 1, I see that this is z by, so again you recalling the expression for the translation of the function, I get that this is z times f of z minus f of 0 plus 2 times f of z times is equal to n times the Z transform of 1, which will be z divided by z minus 1. Well, well, there is a slight change here. I see that this is n times 1. So my expression is the Z transform of n times 1, I can write it as n times 1 to the power n. So I need to take out this n completely. So I get that the right hand side is z by z minus 1 square. So that is the Z transform of this expression, n times 1 to the power n. Okay. So I am also given that f of 0 is 1. So let me just plug that, and let us just simplify. Let me call this 2. I simplify 2 to see that this is also z plus 2 times f of z minus z. So, that is also equal to z divided by z minus 1 square. Okay. So, if I were to simplify all these expressions, let me just do that. I am going to get f of z equals z divided by z plus 2 plus z divided by z plus 2 times z minus 1 square. Okay. So, then all I have to do is, let me call this expression 3 and I am going to apply my inverse Z transform to this 3, and I see that this is also f of, let me call this f of n. Let me start applying the inverse transform of the first expression plus the second expression. Notice that I can rewrite the second expression using my method of partial fractions. So, I am going to break it down into two simpler fractions as follows. So, this is also equal to 1 by 9 times z divided by z plus 2 plus 3 by 9 times z divided by z minus 1 square minus 1 by 9 z divided by z minus 1. So, here I have directly provided you the answer after breaking this rational function into 3 partial fractions. So, students are requested to check that the sum of these 3 partial fractions indeed gives me this final result, this expression. So, I have broken it down into 3 simpler expressions for which I know the Z inverse. So, let me just calculate the Z inverse one by one. So, I see that f of n is the Z inverse of this quantity. So, this is, well, I see that there is 1 by 9 times this quantity and 1 times this quantity. So, that becomes 10 by 9. So, 1 plus 1 by 9, 10 by 9, Z inverse of this factor. So, I see that this particular factor is negative 2 to the power n, negative 2 to the power n. Okay. The other two factors, I can immediately evaluate the last expression. The last expression is negative 1 by 9 times 1 to the power n. Okay. So, that is the Z transform, and the third expression, the Z transform is 3 by 9 times n 1 to the power n. Okay. Now, let me just simplify this complete expression to come to the answer. I see that this is also equal to, so f of n is given by 1 by 9 times 10 negative 2 to the power n plus 3 n minus 1. Okay. So, that completes the answer to this problem asked. Okay. So, that is the final simplified expression for the question. So, let us move ahead to more examples.